Why do we struggle so much when learning linear algebra? I think that the main reason is that we don't have a visual animation to guide us along the way. Take the definition of an eigenspace. A lot of questions may pop into your head. What does IV mean? What does V to V mean? We can't break down a statement to understand it when we don't have a clear picture. In this article, I will guide us through the concept of unitary operators by examining how we evolve a quantum state through time. In quantum mechanics, the quantum state psi is the central object. Within it, we can extract physical quantities such as position, momentum, and energy, etc. Our quantum state is represented by a ket psi in the appropriate state space, V. For instance, if there are three energy basis states, E1 through E3, our quantum state is a linear combination of these three states, where the CJs, the coefficients, are in the appropriate field. For convenience, we'll choose the field to be real numbers. We may write psi in the energy basis as the coefficients in a column vector like so. But given an initial quantum state psi 0, how do we predict the quantum state after, say, 3 seconds? In other words, can we compute psi of 3? Let V denote our state space above. Clearly, the dimension of it is 3. We may define a time evolution operator, ut on V, given by u of t1 acting on psi of t equals the ket psi of t plus t1, where t1 is just some real number. We can show that ut1 is unitary by checking the adjoint property. The following is the proof for u1. The probability of measuring the K state is the following inner product squared. Time evolving psi would change the coefficients from C of 0 to C of t1. We'll see how they change in part 4. Note that E1, E2, and E3 must be an orthonormal basis, since finding a basis state in another is impossible, and the norm of each state is 1 by convention. Hence that the inner product of EI with EJ is the direct delta function of IJ. By intuition, time evolving psi of t shouldn't affect the norm, or magnitude, since finding a state in itself always has 100% probability. So we have that U adjoint U equals the identity, hence showing again that U is unitary. Furthermore, the adjoint of time evolving by t seconds corresponds to time evolving backwards by t seconds. In R3, we represent a unitary operator with a rotation along a particular axis W curve, where W is a subspace of R3 with dimension 2. Vectors on this axis map to themselves, so U of C equals Z for all C in the subspace W, hence C has an eigenvalue of 1. We may choose W1 and W2, both vectors in W, to be orthonormal. That is, the inner product of W1 with W2 is 0, and they span the subspace W. And the condition that the norm of W1 and W2 are both equal to 1. The angle of rotation alpha is a real number such that U of W1 equals W1 cosine of alpha plus W2 sine of alpha, and then U of W2 equals W1 times negative sine alpha plus W2 times cosine alpha. I've chosen W perp to be the span of C, where C is the vector 1, 0, 2, and I've chosen two vectors in this basis to be 1 over root 5 times the vector negative 2, 0, 1, and the second vector to be 0, 1, 0. Let the visuals guide you. Now notice that rotating by 2 pi radians doesn't affect the input. From here we can obtain the fact that a rotation by 2 pi gives you the identity. Furthermore, a rotation by pi gives you the negative of the identity. The composition of unitary operators is also unitary. Geometrically, the composition of 2 rotations is also a rotation. As in the GeoGebra file, we're going to let the matrix UT be the one shown here. Applying U to the initial state, psi of 0 equals 1 on root 3 times the vector 1, 1, 1. As shown in red, we get psi of t shown in blue. The variables d and d prime are the norm of psi 0 and psi t respectively. Notice that they're both 1, and this inequality means that U is a unitary matrix. U adjoint is shown on screen now, which the reader can verify that it is U inverse. For example, when t equals 0.3, the adjoint of U is this matrix right here, and the original U 0.3 is this matrix shown here. Although this rotation preserves length, it changes the coefficients of psi. C1, the coefficient of the first basis state, now changes in time according to the following function. The vector p, shown in purple, is the projection of psi of t onto psi of 0. We've learned in linear algebra that the projection of a vector a onto another vector b is a dot b divided by the norm of b squared times the vector b. So we can apply that to our projection p. So it's going to be the inner product of psi of t with psi of 0 divided by the norm of psi 0 squared times the vector psi 0. The logic variable k shows that the inner product of p with psi of t minus p is they're orthogonal, so we can say that p is the orthogonal projection of psi of t onto psi of 0. So that was my way of learning linear algebra. If you have any problems with things that I've just said, or you think that this method may not be the most suitable for you when learning linear algebra, please leave a comment down below. I'll see you next time.